Hi, welcome to the Cosmic Pie podcast. So I'm your host, Wayne Barkhouse, and today I'm with
Robert Moore. Nice to meet everybody.
Hey, Robert. So we're broadcasting live, as you know, from the campus of the University of North Dakota.
Yep.
And we had a little bit of a technical trouble to start with, but hey, that's technology, right?
Right. Lord.
If you have any questions during the podcast, feel free to send us a live chat, and we'll answer those questions as soon as we see it popping up. So today, Robert, we're going to start with actually a discovery that was made by an amateur astronomer just a few days ago.
Ah,
And
nice.
that is the discovery of a new supernova in a relatively nearby galaxy. When I say relatively nearby, I mean astronomically speaking.
Well, other than the small and large Magellanic Clouds, yeah, galaxies are pretty far apart.
And given the size of the universe, this is very nearby.
This is nearby, yeah.
Right. How nearby, right? So it's just over 20 million light years away.
Okay.
And what was observed was, as I mentioned, a supernova. So this is an exploding star. Now, there are two main types of supernovae. They're the ones that come from the end state of a massive star. We call those a core collapse supernova. Those are so-called type 2 supernovae. And there are some subvariants of them, but we won't get into technical of what they are. The other one is the one that comes from the explosion of a white dwarf. So this is the end state of a low-mass star. In fact, a white dwarf is something that our sun will turn into at the end of its life, roughly 6 billion years, give or take a little bit from now. And so what happens in the case of a white dwarf is that if it accumulates enough mass, and that mass is about 1.4 times the mass of our sun, that white dwarf is not able to resist the gravitational collapse of that amount of mass. And so what happens is it essentially implodes, is a good way of thinking about it, and the whole thing blows up. That is, the whole white dwarf blows up as what we call a carbon detonation supernova, also known as a type 1A.
Right.
Okay. Now, the interesting thing about this particular type, this supernova that went off in this galaxy, by the way, the galaxy's name is the Pinwheel Galaxy. It's in the constellation Ursa Major, but that's commonly referred to as what?
The Big Dipper.
The Big
That's
Dipper.
an asterism.
Exactly.
Remember that word.
Right. And so the Big Dipper is one of those things that people like, if you're living in the Northern Hemisphere, of course, right? If you're in the Southern Hemisphere, if you're in Australia, and you're viewing this podcast, first of all, thank you.
Right.
And for anybody who is viewing this podcast, please give us a thumb up. Okay, we like those.
We like those, yes.
So if you're in the Northern Hemisphere, the Big Dipper is close enough to the pole star, the North Star, so that it's circumpolar. So any given night, if it's clear, if you go outside, you'll be able to see the Big Dipper. So the supernova that went off a few days ago is in the Big Dipper. It's actually a core collapse supernova, type 2. Okay. And the interesting thing about it is when you look at that supernova, so if you had a telescope, you don't need a large telescope to see the supernova. It's actually fairly bright. But the light that enters your telescope, let's say you went out tonight to look at this supernova, then the brightening of this object, that light left that object roughly 21 million years ago. And it's taken that long for the signs of the explosion to reach us here on Earth.
Right.
So when people ask you, when did the explosion happen? Well, it was noticed, roughly a week ago. But yet when you think about the time delay, it actually happened, over 21 million years ago.
And this is kind of like, you might see a car coming around a curve, you'll see it. Anyway, what I'm trying to say is it's because there's a finite speed to the speed of light. It's not infinitely fast, so there is a delay between when it happens and when we finally get to see it.
Right, and just, we always have that delay, so even if you're talking to somebody across the room, you're not seeing them as they are right now in your present, you're seeing them as they were in the past, but in the past could be several nanoseconds, but it's still in the past.
Right.
Unless they're somehow sitting in front of your eyeball, like right against your eye, right? You're essentially seeing them in the past.
And you're hearing them a few microseconds after that.
Right, because it takes sound that long to cover that distance, right, in typical size of a room. Now, what does this actually look like in terms of the Pinwheel Galaxy and what the supernova looks like? So, Robert, if you want to bring up the first slide, we actually have an image of it. Woo-hoo. So here's the image of M101. So M is the Messier catalog. So this was the catalog that was first made, I think it was in 1600s,
Something like that.
right?
I got a funny story about the Messier catalog, but I'll get to that in a minute.
Right. So the idea was Charles Messier was the one who put together this catalog initially, and what he was interested in looking for comets.
He was interested in looking for comets. Keep
Now,
that in mind.
a nickname for a comet is a fuzzy star,
Right.
because when you look at a comet in the sky, and he was using a telescope at the time, they look like a star, stellar nucleus. Not all the time, sometimes, and they got this fuzz around it. So it's the coma part of the comet. And so to make sure that he was seeing comet, and he was in particular looking for a new comet, of course, and to make sure that he was seeing something new, he would write down the coordinates, that is the position in the sky, anytime he saw an object that was not a comet but was comet-like in nature,
Was a fuzzy object.
a fuzzy object. And so this particular galaxy is 101 in that catalog, so it's given that name, M, for the Messier catalog 101. And you can tell, and when you look at this galaxy, notice sort of towards the left of center, you have this red arrow pointing to a particular object. That's the supernova. So the supernova is brightening now, so it was actually caught relatively soon after it exploded and before it reached peak brightness.
Nice.
And so
That's
we're
where
actually,
you want it to.
which is what you get a lot more scientific information on the supernova itself if you can catch it before it reaches maximum brightness. So if you can catch it before it's sort of in that declining stage where its light will decrease. And so we're actually watching the supernova over time now actually increasing in brightness until it reaches its maximum sort of brightness, and then we'll see a decline that'll be viewable for months and months depending on the size of the telescope.
Yep.
But this, like I mentioned before, this type of supernova then, because someone took a spectra of it already to verify which type of supernova it is, and it is a type 2, one that comes from the end state of a massive star. So it's something, a star that would have a mass greater than about 8 times the mass of our own sun when they're on the main sequence, sort of the first stage in the life of a star, converting hydrogen into helium in their cores. So our sun will not become one of these type of supernovae. In fact, because it's isolated,
It won't become any
it
one
won't
of the
become a
others.
supernova at all.
Right.
Yeah.
And it would have to acquire quite a bit of mass because the white dwarf it'll form is going to be about half of a solar mass, and it needs to get up to 1.4.
Yeah,
So
see,
1.5 times. So it's got quite a bit of mass it's got to acquire.
yeah, that's right. So it would have to be a tremendous amount of material had to be dumped on our sun in the future. So in other words, our sun will go out with a whimper and not with a bang.
Well, not with a bang.
If you think of it that way.
Can I tell
Yeah,
a
go ahead.
funny story about Messier?
Sure.
Okay, Messier was a comet hunter. That's why he was making this catalog of fuzzy objects, right? And the funny thing is because of that, he wanted to be known and famous for finding comets, right? But what is he known and famous for?
What?
His catalog of not comets.
Oh, right.
So he wanted to find comets and be famous for finding comets. And instead, what he's famous for is his book of not comets.
Right, touche.
So be careful what you do when you're looking for what you want,
In other words, be careful what you wish for. So
Be careful what you wish for. You might get it, but not the way you want it.
Right. Now, it just so happens coincidentally that there's been another story in the news related to supernovae. So if you want to go to the next
second
item.
slide?
Yes,
Okay.
please. So this was a paper that was published recently, the published date being the 17th of this month, May 2023. And you can see from the title, it is the radio detection of a type 1a supernova. So this is the one that comes from the white dwarf, right? The carbon detonation type of supernova. And the idea here behind this is that people try to determine then what is the object, what is the beast that blew up to form the supernovae. So it's okay, you can say the simple story where you have this white dwarf, material transfers on top of the white dwarf. And by the way, the white dwarf, even though you can think of it as a star, it's not a real star in a sense that is undergoing fusion reactions in its core.
It's a cinder.
That's right. It's at the end state of a low mass star. And so it's made up of mainly carbon with some oxygen. In fact, some people hypothesize that it would take on a crystalline type of form So in some sense, it would be the purest diamond in the
Purest
universe.
diamond. Wow.
It's just a matter of going there, grabbing a sample, and bringing it back to Earth and selling it. But don't bring back too much, or you flood the market. You have to be
Right.
careful, right?
And not only that, but good luck finding a material that could lift it off.
Yes, that's right. Well, that's the hard part. How do you get that
Yeah.
back to the Earth to sell it, type of thing? And so these objects then, what happens with time is that they essentially cool down until they reach the background temperature of outer space, which today is on the order of about 3 Kelvin.
Right.
Okay, that's extremely cold temperature, minus 269,
-200,
minus 270 or so Celsius, and
Yeah.
minus 400 and some odd Fahrenheit.
Right.
So even in North Dakota in January, where we live, that's
It's about the same, isn't it?
your
Sorry,
car
no.
would definitely not start if it was that cold outside, minus 400 degrees Fahrenheit. Yes.
You'd have to bundle up pretty good for that one.
I wouldn't be walking to work either in
Yeah.
that kind of temperature. I think it would be solid. So yeah, so that's even cold in that case. So the future then of our sun, and you think of 10 billion years from now, would be just to gradually cool off to that background temperature. And of course, that background temperature is declining all the time, slightly,
Right.
because the universe is expanding. And so that leftover heat from the Big Bang, which is the background temperature of outer space, right, is certainly decreasing. Of course, you have your ambient star field that would give off,
Right.
energy. And
Like the temperature inside the solar system is a bit warmer than that because
That's
you've
right.
got a star nearby.
Yeah, exactly. And you can even figure in the planets give off radiation too in the infrared, so that would be a heating effect as well.
Well, especially ones like Jupiter and Saturn,
That's
which
what I'm
are still
thinking.
collapsing.
That's right. Yeah.
So
That's
there's
right. There's
still
still a-
gravitational energy being released.
Yeah, there's still a net source of energy that comes out of those objects.
Right.
So these type of supernovae, the very simple model is one where you just transfer material from a nearby companion star on top of the supernovae. If it reaches that limit of 1.4 times the mass of our sun, then the whole thing blows up. It can't hold up the weight, as some people think of it. It's the mass, really. It can't withstand that gravitational field of trying to collapse the object.
Yeah.
So it collapses in on itself.
I mean, one way of looking at this is a star on the main sequence is being supported against gravity by radiation pressure. When it collapses to a white dwarf, it's being held up by electron pressure because electrons repel each other and they create a pressure.
Right.
If the electron pressure is overcome, you get a collapse.
Yeah, think of putting heavy, massive objects on the roof of your house. And
Yeah.
keep adding masses. And you do this thought experiment, could I do that forever? I keep adding like lead balls or something.
Right.
And imagine these lead balls could be extremely tiny, but they're very massive. Each one weighs 10,000 pounds. And you keep adding these lead balls so there's enough room on the roof to do this. How many do you add before the roof just collapses?
There you go.
And that's it's not exactly, it's an analogy, of course, not all, every analogy has some defects in it, right? They break down at some point, right?
Right.
So the idea is you can add little pieces of mass to a white dwarf. How much mass could you add to a white dwarf before it would collapse due to its mass?
Right.
And that's the 1.4 solar mass limit.
And it's because it's that sudden collapse that it then rebounds and explodes and destroys itself.
Right. That limit was actually calculated way back, almost 100 years ago
Almost
now,
100.
back in the 1930s by Chandrasekhar. And so-
Chandrasekhar Subramaniam?
Yes, exactly. So the Chandra X-ray Observatory is named after him, and he was a brilliant physicist, won the Nobel Prize in physics as well. He spent a lot of years of his career at the University of Chicago.
Right.
And the story goes that he worked on the material that a white dwarf would be made up of, the fancy name being this degenerate material. And he did this experiment of adding masses to a white dwarf and understanding what would happen. Could he continue that forever? And he discovered no, that there was this limit. And that's something that he did while he was in transit, and this by boat, essentially, from India to England.
Right.
And so it took several weeks for that journey back in the 1930s. So I guess I like to joke and say instead of being on the top of the deck, sunning himself or something, right, or chatting away or drinking.
He was in his room.
He was in his cabin,
scrawling equations.
Yeah, that's right, doing the equations in his room, and won the Nobel Prize for it ultimately.
Yeah. He's another one. I've seen pages out of his notebooks that he was doing those calculations in, and it's a scary notebook. To be
Right.
honest.
Highly intensive mathematically speaking.
Good Lord, yes. Wow.
So yeah, so the kind of very simple model then is to have material then that gets transported to or transferred to a white dwarf and then exceeds this limit, then it blows up at this carbon detonation supernova. Some people ask what's left over behind, and why they ask that is because the other type of supernova, that is the end state of a high mass star, a lot of times what's left over are these neutron stars and even black holes.
Or black holes, right.
So you ask what's left over from a type 1a, and as far as we can tell, there's nothing left over. The complete white dwarf itself, all through its whole interior, explodes. There's nothing that remains, right? So you can imagine all this debris flying outwards in the explosion itself.
And again, it's because of that stuff is falling in on it to make it a sudden collapse instead of a compressional collapse like forms a neutron star or something.
Yeah, so the explosion then gets transmitted right through the whole object itself. Mm-hmm. And for a massive star, it's really outside of that core of neutrons where the explosion, this core bounce that occurs, right?
It hits the core, and the core is so dense it just bounces off.
Right, so the core itself usually is maintained, and it's just whether or not it's dense enough to ultimately collapse into a black hole or maintains its structure to become a neutron star. But that's for the other type of supernova. So that's interesting then, a very simple type of model that we have for these type 1a supernovae. But the thing to think about it is that always the case? So anytime a supernova goes off, the best thing you can do is look in detail at its spectrum, and from the appearance of the spectral lines, you can tell which type of supernova it is.
Right.
So if it's a type 1a supernova, so the progenitor is the white dwarf, are all these type 1a supernovas identical? Absolutely identical.
And that's a good question.
It is a good question, but anytime you look at a population in science, it could be a population of elephants, or it could be a population of people that you're studying in biology or whatever, or maybe it's a population of stars. There's always going to be discrepancies when you look close enough at the details. In other words, even at individuals, if you look at a population of people, you know that people are individuals. They're not all absolutely identical.
Right.
Now, from afar, or just a very coarse looking or study of people, of course, you can see very large similarities. Mm-hmm. People got two legs in general, they got two arms, and they walk, they got two eyes, they got two ears, so on and so forth. But if you look in really nitty-gritty fine detail, you can look in such detail that eventually you could study each individual human being as their own unique human, in that case, right?
And I agree, yes.
Right. Well, the same thing can happen here. When you look in detail at these supernovae, these type 1a, what we find is there's a range in properties. They're not all perfectly identical. And so the range in properties is something that's actually interesting, right? You want to know, why is that particular type 1a supernova not identical to another type 1a supernova? What caused those differences? And those differences, as I mentioned, could be subtle. Mm-hmm. Okay, so there have been various models that have been proposed to try to explain these differences. This paper that came out in Nature the other day is the first detection of a type 1a supernova in the radio.
That's neat.
Okay, so this is the first time. So up to this point, no prior type 1a supernova had been detected at radio wavelengths.
They're so energetic that the shorter wavelength, the higher energy wavelengths overwhelm any radio signal, correct?
Right. Yet, well, the thing is that you might think of, why would you see radio?
Right.
And so if you have thermal emission,
you'd see infrared.
Right, you're going to, well, it depends on the temperature of the object, right? So in the explosion, you have very high temperatures, so you're going to get a lot of ultraviolet photons that get emitted, and X-rays and so on you expect. But the radio is expected to come from any type of debris that surrounds the white dwarf itself. Okay. Now, one of the questions that's asked about Betelgeuse, so this has been in the news in the last several years because a few years ago, just prior to the onset of COVID, right? So there's, you always divide time, like I always say,
post-COVID and pre-COVID.
Exactly. This was pre-COVID, where Betelgeuse dimmed significantly in the sky. Yep. And people said, it's ready to go supernova. Well, Betelgeuse is a high mass star, so it would go core collapse supernova, the type 2 type of supernova. And so we know it's going to occur. It has enough mass that it's definitely going to turn into a supernova, a type 2 core collapse supernova. The question is, when will this happen? And we just don't know. It could happen tonight, or it could happen 10,000 years from now.
I was about to say it's going to happen soon, but that's not soon on human lifetimes. That's soon astronomically. So,
Right, so don't go bet that it's going to happen in the next 10 years. Don't put a lot of money on that.
right,
You know?
right.
But then again, if you're right, you should get a lot of money back,
You should.
right? So the betting would be good on that. So the type 1As then, in order to explain the variation in the properties that we measure, people have come up with very complicated models. So here's an illustration of that. So this is a chart that illustrates a possible route or scenario to reach a type 1A type of explosion. So how would this happen? So if we start at the very top of the panel on the far left, what you see here is two normal stars that are in orbit around each other, what we call a binary star system. Now, it turns out that, as far as we can tell, most stars in our galaxy, and by extension probably in other galaxies, they're not isolated like our own sun. Our own sun is in the minority in that case. Most stars seem to be in a binary type system, or at least multiple star systems.
Right.
And the reason for that is it's related to the formation process. When stars initially form, they usually formed in an association or in a giant molecular cloud in which you could have several regions that ultimately have a density high enough, that is, they have the right conditions, that gravity can cause those objects to collapse to the point where nuclear fusion can occur. So they need to reach that core temperature of 10 million Kelvin. Now, so to allow hydrogen to fuse into helium. So probability-wise, you would expect that stars would form in a little community, or at least in some type of community.
Mm-hmm.
And so that's why, as far as we can tell, that at least a majority of stars have at least one other companion star.
And that's in fact what we see. We call them open clusters. So, yes, they form in groups and associations and clusters.
That's right. So the sun is a little bit unique in that sense that it's just the sun.
Right.
And as far as we can tell, it didn't have another sibling. Now, it may have formed in a loose, bounded type of system early on, let's say 4.5 billion years ago, and the other stars or siblings to our sun have escaped the region around our sun as we orbit the Milky Way, and they're on their own independent orbits around our galaxy.
Right.
And by now, we've gone around the Milky Way roughly 18 times since it's formed. So those siblings, the brothers and sisters to our sun, they could be on the other side of the Milky Way.
I like to point out on that one that from the geology, we can hypothesize that we were in an association at one point, because there's evidence from the isotope ratios that there was a supernova that occurred before the sun really went onto the main sequence, when it was still young. So if that was the case, it had to be nearby, and thus we had neighbors at one point.
Right, so that's the aluminum 26 measurement.
Absolutely. Very
Yeah.
nice. Yes. I wasn't sure if you knew about
Yeah.
that. Yeah, it's the aluminum 26.
The problem in all this, of course, is you want to find the siblings to our sun. That's an interesting, just to go on a little bit of a side here. So what would you look for? Well, you want compositionally something to be identical to our own sun. And so you can look at, a spectra of millions of stars in our own Milky Way, looking for something that's absolutely identical to our own sun. And so far, we haven't found any, right? So then we need to look for this kind of stuff. And so far, no joy, right? We haven't detected any siblings to our own sun.
I hope we're not having technical issues. I'm getting a flashing light. That's why I'm looking. Sorry.
Okay. Anyway, so the other thing is, so getting back to the type 1A supernova, in the panel that you see, notice that we have a situation where you have two normal stars are in this binary type system. That's extremely important. Why? Because the white dwarf that ultimately turns into or explodes as this type 1A supernova, it needs to have matter transferred on top of it, so then it reaches that 1.4 solar mass Chandrasekhar limit. So the question becomes, how do you get that material? Well, that would come from a nearby close companion star. So we know that during stellar evolution, the more massive a star, the faster it goes through its life cycle. So you could have a situation that you see here in this panel in the top, on the upper left, that one star is more massive than another. And the more massive star, which is sort of in the middle of the top panel, the more massive star has evolved beyond the main sequence. It's now turning into, let's say, a red giant, and it expands in size. And as that star expands in size, become a red giant, then matter gets transferred on top of the other star, the low mass star. And that will cause eventually, if enough material to be transferred over, that this white dwarf or this other normal star will accumulate enough material that if the other star turns into a white dwarf, for example, that the lower mass star becomes a red giant, material can be transferred on top of the white dwarf and cause it to reach that Chandrasekhar mass limit.
I'm going to interject here. I see we are definitely having trouble, so I'm sorry for the drop frames and everything that's going on. We are having technical difficulties with our internet connection.
Yeah, the internet connection today is not good. It must be cloudy out all of a sudden.
It must be or something.
Yeah.
Because I've never seen it behave like this.
Yeah, so we'll push on and see what happens. So in this type of situation then, that's sort of the main thing, right? That one object turns into a white dwarf. The other object that's in the binary star system reaches the point where it has increased in size to become a red giant, and matter transfers on top of the white dwarf, allowing the white dwarf eventually to reach that Chandrasekhar limit and blow up as a type 1a supernova. Or you could have other situations that this graph actually illustrates. So in this case, notice the more massive star then transfers material on top of the other star, but the other star is not a white dwarf. And so what can happen is these two stars actually can then orbit inside this common envelope of material, the circumstellar envelope that the binary star system is orbiting within. And eventually that material gets cleared out. One of the star then, as you see here in the bottom row of this diagram, transfer mass back onto the other star that has become a white dwarf, and then eventually it goes carbon detonation supernova, this type 1a. So we can have various scenarios that can get extremely complicated. Now, the type 1a supernovas are very important in the history of cosmology. Now, Robert, why is that?
Well, the main one I know, because I did a presentation on their winning of the Nobel Prize, is that it was the first indication that we had that the expansion rate of the universe is not constant, but is actually accelerating.
Okay, so if it's accelerating, how do they know that? What's so special about these type 1a supernovae that allow you to deduce that?
Because they explode when they reach the Chandrasekhar limit. That means all the explosions are about the same size, which means they're the same intrinsic brightness, which, again, brightness falls off as 1 over the distance squared. So if I know how bright it is, and I know how bright it appears to be, I can tell how far away it is.
Right, so it's like you had 10 identical sticks of dynamite, and you light one off at a time, and you measure how bright they become, the maximum brightness during the explosion. Right. And if they are truly identical, they should have the same brightness.
They should have the same brightness.
And that's really what we mean by luminosity in this case, right? Their intrinsic brightness, their wattage, if you think of a light bulb. So these type 1a supernovae, they can be located at various distances away from us. They could be in our own galaxy. They could be in other galaxies. As long as we can tell they're type 1a supernovae, then we can use them to measure distances. If we can make that assumption then that these supernovae then can be calibrated so we know what the luminosity is of their peak brightness.
Right.
Then that allows us to use them by measuring what is the apparent brightness of the peak of the explosion and compare it to the intrinsic brightness. That those two values differ according to how far away these supernovae are. In other words, we have an independent way of measuring distance. And it was from those measurements of distances to various supernova type 1a in different galaxies that allowed us to deduce that the expansion rate of the universe is accelerating. That's the dark energy.
Right.
Okay. Now, with these observations then of looking at the radio emission coming from a type 1a supernova, looking at these different scenarios that ultimately would result in a type 1a supernova, some people get worried that we don't know supernova type 1a as well as we think we know.
Right.
And therefore, how do you know for sure that we've calibrated their peak brightness in the explosion properly? How do you know there's not some uncertainty, some variation in those values?
Right.
Well, there's definitely going to be some variation. They're not all exactly like identical sticks of dynamite.
Right.
There are variations. We see the variations in the properties when we measure the spectra. That's what gives rise to other scenarios besides the one that I mentioned, where you just simply have matter transferred on top of the white dwarf, eventually exceeding the Chandrasekhar limit.
The question becomes, in my mind, are they enough different that it makes a matter on these types of calculations? Does it make enough of a difference that it's an order of magnitude, a power of 10 different from each other?
That's right. So you're going to have fluctuations anyways in the properties, the brightnesses of these supernova. Imagine if there's like the graph that we showed earlier, if the two stars are orbiting in a common envelope of material, that the properties of the peak brightness are not going to be exactly the same as if you had just a white dwarf by itself, and then a little bit further away you had another star that was less massive, that went through its life cycle, became a red giant, transferred material on top of the white dwarf, without this common envelope of material, circumstellar envelope of material. So there can be different subtle differences from one to the other. And some people worry, as I mentioned, then that it throws off the distance scale. No, it doesn't throw off. It gives you some dispersion in your measured value, some range in the measured value.
Error bars.
Yeah, it'd be like if you measured your table, right? Let's say you have a kitchen table and you measure it 100 times. And each time you measured it, you're off by 1/32 of an inch. They vary. Now, that's probably the way you're measuring. It's not like your tape measure shrunk or in size, right? It's probably because your head is tilted slightly different angle when you're making that measurement, and so on and so forth. And so you just take the average of those values. That would give you a better approximation to the actual length of your table. So you would state the table is a certain length, plus or minus that range in values is one way you could denote the uncertainty in your measurement or the error in your measurement.
Right.
So all numbers in science then have this uncertainty, this inherent range, and we need to appreciate what that range is. So in this case, as far as we can tell, the uncertainty in our distant measurement doesn't come close to dispelling the dark energy.
Right.
All right, by using these type 1a supernova, right? So that'll just all eventually boils down into the uncertainty of the amount of dark energy, the accelerated expansion of the universe.
It's still there. It's just a question of how much.
That's right, and to know its precise exact value, right? How far off are you on that? But we have other techniques that we use to measure the accelerated expansion of the universe, not just the type 1a supernovae.
Right.
So it was interesting a few days ago that I noticed a science journalist made the remark that because we don't fully understand the type 1a supernova, they're more complex than what we initially assumed, that somehow that may translate into a question mark as to the existence of dark energy to begin with. And that's totally false, because even if you dismiss totally the use of the type 1a supernova to measure distances and therefore to imply the existence of dark energy, let's just throw that out. There are other techniques that have been developed since the late 1990s that we can use to measure dark energy, and they all give the same sort of thing. Dark energy exists, and this is the amount.
Right. It gets into that whole thing of, you just, because you don't know one thing, okay, we can throw it out, but there's still these other piles of evidence that say, hey, this is going on,
Yeah, I mean, that's the way science works. You want to refine your techniques. In fact, by studying these supernovae of type 1As in different environments, that may eventually lead us to the position where we understand them very, very well, and actually we can correct. We go measure the type supernova, see that it's a type 1A, measure the correction, and we have a very precise measurement of the distance.
Oh,
that would be a great
actually
day. can refine our measurements of dark energy, maybe to the point become much more precise.
That'll also refine our models for stellar evolution and everything else. So this would be just great information to have. I mean, yeah.
Exactly. So, I mean, science is always a work in progress, and this is no exception.
Bingo.
Yeah. So, Robert, you had some interesting stuff that you wanted to talk about, changing gears a little bit here.
Mine changes gears completely. I mean, this is like throwing it in reverse. Basically, I saw a story about Earthshine on the moon.
Did you say moonshine?
Sorry. No, not moonshine, Earthshine.
Oh, okay.
And so what Earthshine is
you had me thirsty there for a second.
Sorry. The Earth and Moon, the Moon is not the only astronomical object that...
Is it time to put in a disclaimer?
Oh, yes.
Go ahead.
Is not the only object that reflects light. The Earth does as well. In fact, it reflects about 30% of 33%, sorry, of the solar light that falls on it, at least at the moment. So that light is reflected off of the Earth. Some of it hits the moon and is reflected off of the moon and comes back to Earth. And so you've got this phenomena called Earthshine. And I took one image of it one time, and it's got some interesting factors I'll discuss when I show it. So this was a 2-second image of the moon. And you can see quite clearly that the side that was unlit, the dark side, is still clearly visible. Well, that's due to this light that's reflected off of the Earth back onto the moon. So what causes these crazy arcs of color on the left side? And the answer to that is I thought I had it positioned so that all of the bright side of the moon was out of the picture. But apparently what happened is I had a little mountain peak that was still brightly lit right on the edge of the eyepiece hole, the aperture for the camera. And so this creates diffraction, which splits the light up into a rainbow, and thus you've got two rainbows that are going on in that picture. That's why I've kept this picture, really, because it's really an error, but at the same time, it's a neat fluke that happened to just work, and all the alignments happened to work just fine. But go ahead.
I was going to say, and you mentioned the dark side, so the thing to note here is that at that moment in time when Robert took this picture, this is the dark side of the moon.
This is the dark side.
We're not referring to the back side of the moon
Right.
as being the dark side.
Right. Because there is no side of the moon that is totally dark all the time. It's just dark. The opposite side of the moon to us is dark in that we don't really know it as well because we don't see it unless we send a spacecraft up and around it, because only one side of the moon faces us at any time. It's called tidal locking. Maybe that's a topic we ought to bring up sometime, is go into tidal locking and what it'll do.
In other words, the side of the moon that's dark is the one that's not in sunlight.
Right.
Just like here on the Earth, nighttime, the sun is below the horizon.
So what's going on in this picture is that side of the moon is being illuminated by Earth, not by the sun. Like I said, this is a 2-second exposure. So for reference, your eye takes about 20 frames a second. The refresh rate on the chemicals in your eye is about 1/20th of a second. So your eye takes 1/20th of a second exposures. This is 2 seconds to get it looking that bright. If you want to see what the bright side of the moon looked like on that same night, this is the same night. This is 2/10 of a second, so about what your eye takes of the bright side of that same moon. So why is it orange then? Because I took the pictures when it was pretty low on the horizon, so it was scattering most of the blue light still.
And the thing to note too, so you were mentioning if you go back to the last one that you showed, so you can see the part of the moon that's in darkness, that is, sunlight is not hitting it directly, but it's the light reflected off of the Earth from the sun that reflects off the surface of the moon and then back to us.
Right.
We can see it. And so it's like the situation where you go outside during a full moon at night.
Yes.
Right? And you can see because you have the moon. Now imagine that you're on the Earth. Imagine that you're on the moon when the Earth is shining light on the side of the moon that's not in direct sunlight. The Earth is much bigger than the moon itself and therefore brighter because of the reflection off the clouds and so on.
Not only that, but I'm going to get into this in a second. The Earth is actually much brighter. Like I said, the Earth reflects about 33% of the light that falls on it. The moon only reflects about 17%. So let's take a look at that. These are Earth samples, but they're the same type of mineral that the rock that the moon is made out of. And they are basalt on the left and andesite on the right. And so the bright side portions of the moon are made out of this right-hand material, and the mare, are made out of that black material. So the moon is actually made out of pretty dark rock. Well, why is it so bright then? I mean, 2/10 of a second exposure gives me this. Well, the answer is because the moon is relatively large and really close. And so the Earth is actually much brighter than the moon because it is much larger still, and it actually reflects more light. Think about clouds. So I like that story because a lot of people don't realize about Earthshine. And I like to also bring up another thing I looked up, because people in astronomical images, especially of the moon or from the moon, often go, well, where are the stars? Well, the answer is your eye is much better than any camera that has ever been invented, period. End of story. Your eye, they measure the brightness difference that the camera can pick up in what's called stops. The best cameras are about 15 stops, which the difference in brightness between one stop and the next is a factor of 2. So a 2 stop is half as bright as a 1 stop. So the best cameras are 15 stops. So if you're looking at a bright object, you are not going to see something dimmer than about 2 to the 15th times dimmer. The stars are much dimmer than the moon. We're talking on the order of powers of 10 difference. So what about your eye? Your eye is 21 stops. So your eye can actually see different levels of brightness to a much higher degree than even the best cameras. So how well can you see the stars with your eye, which is much better than any camera? How well can you see the stars around a full moon? And the answer is, I guarantee you, you can't. Because this is why we don't like doing astronomy on full moon nights, because even far away from the moon, it washes out all of the stars. Mm-hmm. It's just too bright. But anyway, that kind of moves away from this topic of Earthshine, which you can go out and see anytime most of the moon is unlit, by the sun anyway. You can actually see it with your eye, because again, the bright side of the moon is not much dimmer than, or the unlit by the sun side of the moon is not that much dimmer than the bright side of the moon. So your eye can actually pick up both. Cameras can't.
Yeah, so it's the difference in another way of saying about it, the dynamical range.
It's the dynamic range. Thank you. Yes, that's the term I was trying to look.
Okay, yeah.
And your eye simply has a much better dynamic range than even the best cameras out there.
Right.
And your eye also has a much better color resolution than even the best cameras out there. What do I mean by that? Your eye brain system can detect and process millions of times more colors. Well, not anymore. Some of the better screens can actually produce that many colors now. But your eye brain, until recently, was much better at differentiating color than even the best video screens.
Well, yeah, I'm thinking of in the future when we return to the moon and then put a permanent base on the moon, there are going to be times when people that are on the moon, if let's say you're on one of the Apollo sites, you're going to have approximately 14 days of sunlight, and then you're going to be dark for 14 days, approximately. So you're going to go through a nighttime that's 14 Earth days long. And during that time, the Earth can be above the horizon.
Right.
And you're going to have that light coming from the Earth that's going to shine on the surface of the moon where you're at.
And as bright as, like we've been saying, as bright as we think the moon is from Earth,
in full moon,
the full Earth will be even brighter.
Even brighter.
So these are things to keep in mind. I mean, to me, this is a holy cow. This is a neat. It's trivial in a way, but it's just neat to think about and to work your brain around that a full Earth seen from the moon is going to be much brighter than a full moon seen from the Earth.
Yeah. So if you're on the near side of the moon base, right, you're not on the far side of the moon, because then you wouldn't see the Earth at all, of course.
Right.
But if you're on the near side, then it's really never going to be nighttime.
Right.
Like we have here.
Oh, that's
right?
a very good point.
When the Earth's above the horizon.
Right.
You have to, right? So if the Earth's above the horizon, then like we have during a full moon, but it's even going to be more so, it's like a really super full moon in terms of the amount of light. It'd be interesting to see what it'd be like walking around on the surface of the moon.
The only time that will not be true is during a lunar eclipse.
Right.
Because then the moon is actually passing into Earth's shadow, and so you'll be getting no light then.
Right, and that just
Are-
happens once in a while. It's not like a monthly thing
Right.
because of the tilt in the moon Earth orbit relative to the tilt of the Earth Sun orbit.
Absolutely. I mean, these are
Yeah.
great things to think about. I find them neat.
So that's going to be, I mean, one of the questions I ask sometimes introductory astronomy students is if you were standing on the surface of the moon, would you notice the Earth going through a series of phases?
Mm-hmm. And the answer should be yes.
It's yes. And you got to think of that because all of a sudden you have to place your mind in somewhere else.
Mm-hmm.
Imagine that you're on the moon and think of the orbital motion as the moon goes around the Earth and then the Earth, of course, is going around the sun, how the alignment changes. What
Right.
would you perceive from the moon?
And due to that inclination of the lunar orbit compared to Earth's equator, I would say the only phase of Earth phase you wouldn't see would be a new Earth, except you would see it in the case of a lunar eclipse.
Right.
But any other time, there would always be at least a sliver of the Earth visible.
Yeah, and in fact, you can look at the Apollo project, look at some of the images that were taken of the Earth from by the astronauts, and most of them show the Earth at some phase. It's not
Right.
usually a full phase, right? It's an intermediate type of phase.
In fact, Apollo 17 was the only one that got a full Earth, wasn't it?
I mean, that was on its way to the moon, right?
Okay.
Yeah, so that's you're thinking about on its journey to the moon when it launched
Yeah.
that night. But even from the surface of the moon, there are images they look up and you could see the moon, see the Earth in the sky, and the Earth was not a full Earth,
Right.
right? It's like a gibbous or something like that. So
Yeah. I mean, yeah. It's cool. It's great.
yeah, so that's in the future when we get back to the moon and hopefully stay. That'll become more commonplace as I'm sure people will be able to tap into live feeds from the moon base.
Right.
Moon base alpha.
And
See what
to
the
me,
Earth-
the neat thing is we'll be able to see all of this because where will the moon bases most likely be located?
Well, right now they're talking about the south pole of the moon.
Right. Because there's been water detected in the deep craters on the south pole of the moon. And water is one of the heaviest, densest elements that you need, that is required. So if you don't have to carry your water with you because it's already there, you're ahead of the game.
In fact, someone could, if you want to be technical, there are places on the moon that are always in perpetual darkness.
Mhm.
And these are places like in the South Pole where they're inside of deep craters and the sun never gets high enough in the sky that light can go directly to the floor of the crater itself.
So why doesn't that ice sublimate? Because there's no atmosphere to keep it there.
That's right.
So why? Why do you I mean, I know some of the reason.
No, I mean, this stuff is buried under the soil, right? So
Right.
there's a blanket on top of
So
it.
there's a blanket on top of it,
Yeah.
for one. And for another type, this is not ice like you put in your glass
Oh,
of
this
tea.
is hard as a rock.
This is
ice.
hard as a rock ice.
Yeah.
You know, this is a different type, a different phase of ice. You know, we think of water having 3 phases. It actually has many phases. And that's just neat in and of itself, too. So the particular phase of ice that it's in, it's so cold and it's so solid, so locked into its crystal structure that it can't actually float off of the surface and
Right.
sublimate.
Yeah.
So,
And that's going to be interesting to see how much is there. I mean, measurements show you one thing, but you need to go down there and do in situ type of exploration to find out what the condition of that water is.
yeah. And
So,
you know, other things that I think are neat is on Earth, what is the most common atomically element that makes up Earth? In other words, looking at it on atom by atom basis.
like the soil, silicon.
No, I'm talking about the whole Earth.
Oh, the whole Earth.
Yeah. The bulk Earth, that is the most common element,
What
atom
is
by
it?
atom. Oxygen,
Okay.
Because-
that's locked up in the silicon.
because it's locked up with the silicon.
Yeah.
Because most of your rock is some form of SiO2.
Right.
Well, for every atom of silicon, which is what you mentioned, there's 2 atoms of oxygen there.
Right.
And why this is important is the moon is made out of similar stuff, basalt and andesite. And both of these are silicate minerals, so they have that SiO2 going on. So you could actually not have to take air with you because you could bake the oxygen out of the rock. Energy intensive, but when you've got solar that you can always have power coming from the sun, who cares how much energy it takes?
Well, as long as you're not in that shadow area, you have to put your
panels
up
in the
high
place.
on top of the rim of the crater
Right.
in
But
order to pick up that.
These are all things that people are looking at. And
Or you just bring thermoelectric generators that run off the decayed plutonium or something like that,
Or
nuclear
TIGs.
power. Yes,
Yeah.
so you don't need solar panels at all. Be more efficient.
the
You
Cree
can
have
answer
base-
that one.
The Cree have a base up there. Is a blue area that has the atmosphere. That's what. Yeah.
I don't even know who the Cree are.
The Cree are Marvel Comics.
Okay.
They're one of the bad guys.
Okay.
But put that in quotes. They've been the good guys at times, and then they're back to being the bad guys, and then they're back to being okay. And yeah, or is that the Scree? Oh well,
I don't know.
it's been a while since I've read my Marvel comics. But
So yeah, going forward, so that's going to be really interesting.
mhm.
The thing is, when we're going to get there, that's the problem.
When we're going to get there. And to me, the other neat thing is another energy source they're looking at for the moon is because of the solar wind that is constantly blowing and striking the rocks. There's an abundance of what we call helium-3, 2 protons and 1 neutron in the nucleus. It's a helium atom, but it's a little lighter. But it actually is easier to create fusion with it. So we could be powering a lunar base with nuclear fusion due to the abundance of the He3, the helium-3 atoms that are up there. So a lot of stuff going on.
So okay. I was going to
Yeah.
make a joke about
Oh.
moon base alpha,
Moon
space
base
in
alpha?
1999.
Blowing
We
it
have
out
all,
of
yeah,
orbit?
have all this radioactive waste laying around that ultimately explodes and the moon goes out
Blows
of
it
the
away.
orbit.
You know, and I don't think the moon will go out of orbit for anything we do there,
It'd be
but
pretty powerful.
that would have to take a pretty powerful explosion. But I will mention that people go, oh, well, solar power isn't an answer because what if it goes cloudy or dark? Well, the neat thing is
On the moon?
on the moon we can build generators, solar panel generators that produce the energy, and then beam it back to Earth via microwaves.
Well, think of it this way. In the daytime on the moon, it wouldn't be an issue, of course. The sun's above the local horizon. But at night, we have 14 days of no sun when it's below the horizon. But the Earthshine is so powerful that if the Earth is above the horizon,
We could still
you
generate.
could use solar panels to generate electricity
Absolutely.
that way.
So, I love thinking about this stuff because these are what the engineers are thinking of. And that brings up the other point that we probably want to get close to tying in on. But this is why we say, join us. Because this is engineering problems. This is physics problems. This is chemistry problems. This is geology problems. Come join us. Figure these problems out. This is neat stuff. And it's not just, working. It's not just working out a bunch of nasty equations. Some of it is actually pretty fun and sitting around a table going like we're doing.
And did you hear the news a few days ago that NASA awarded Blue Origins a contract to build a lander on the moon?
Mm-hmm.
So now there's two. There's SpaceX and now Blue Origins are
Right.
both developing their own lander as sort of a backup to each other in that sense. So NASA is pushing ahead because that's kind of the one ingredient that's been missing up to this point. We built the SLS, or the rocket that'll take us to the moon. That was the launch we had several months ago, last year.
Right.
There's another launch coming up probably next year in which we'll have astronauts that'll go around the moon and come back.
Right.
And then the flight after that is supposed to be an actual landing. But we have no way to land on the moon.
Right.
So it's extremely important that we award these contracts to get these private companies to build their systems and test it fully so we can have something to actually go to the moon and land. But without that, we have to wait.
Right.
So hopefully the testing will go smoothly, the time frames and when we get these landers will not be delayed significantly.
We've done it in 10 years before. So I see no reason why we can't.
It seems like there's always that, yes, we did it before, we can do it again. You always use that euphemism, whatever you want to call it, that, hey, we can get to the moon, we can do X, right?
Right.
People always use that.
It's not necessarily the case.
But we wonder but here we're supposed to be more robust. We're not in a
Right.
big race that we got to almost kill ourselves to get there in a certain period of time before the decade is out or whatever, right?
Right.
Now we can do it and do it in such a way that it's a better system. It's more reliable, hopefully,
Yep.
right? Can carry more cargo. to the lunar soil and back up again.
And back up again.
And so these,
Right.
and they use them over and over again, reusable, right?
Right.
Rather than throwing them away after using them only once.
And we're now to the point that we could actually land ahead of time
yes.
a big package that they could then assemble into a rover car that they can drive around and get further away. We've now got cellular signals, radio signals that we can track so they can actually get out of sight of the lander with that car, if you will.
Well, we just put satellites in orbit around the moon
Right.
and the constant communication
And,
anywhere you are on the surface.
You know, so
essentially.
they can rove a lot farther now. They can do all this extra. All it takes is time and engineering skill and putting it together.
Yeah, that's it. You just need the support. You need the public support. That's
Pardon?
really what you need. You need the
Yes.
public to be able to say it's worthwhile to spend money on doing these things.
Right.
Because that's ultimately the stuff is being paid for by the taxpayer. Even when you have private companies are building things, you're paying the government, in other words, us, the taxpayer, is paying these private companies to
Right.
deliver a product. But if we don't want that product, we're not going to pay for it.
Right. And I've tried to mention some of the reasons we might want that product because it will advance all of our lives. Immediately? No. Down the road? Absolutely. You know, energy production up there could be done easier and simpler, cheaper, and with less risk to health and life and limb. That's the term. And so, yeah, I'm like, why wouldn't we want to do this?
Well, like I said, you never know what happens in the future.
Right.
And so if you don't develop anything, you're never going to develop anything, right? You're stuck in that.
You're stuck where you are.
You're stuck where you are. Okay, so I think that's it for today. We
That
can
sounds
wrap
like
this
good.
up. And remember, the opinions that Robert and I expressed today are our own personal opinions and not necessarily those of the university or the college or anyone else, of course, just in case some of them you didn't like.
Yeah, and just in case, email me, if you don't like what I'm saying.
Now, our next podcast will be on Tuesday, May the 30th. So 1
Right.
week from now. Hopefully the internet will run a little smoother than what it did at the first half of the podcast today. We always leave you with a quote. So today's quote is from Paul Dirac, who's actually the person who came up with, and we either know he didn't realize it at the time, the mathematical expression for the existence of antimatter.
Okay.
Okay? And so his quote is, "A physical law must possess mathematical beauty."
Ooh.
So if it's not beautiful mathematically, and that, depends on your opinion if something is mathematically beautiful or not.
Right.
His statement is that a physical law will usually have mathematical beauty associated with it. And we can do a whole podcast on it. What I was really talking about, I believe, is just symmetry.
Symmetry.
When you look at something that's completely symmetric, it has this beauty, inherent beauty associated with it. And we see symmetry in all the physical laws of nature that we have explored. So if you enjoyed this podcast, please give us a thumb up. Please also see us next time, then a week from today. In the meantime, we'll see you next time. Thank you
We'll see
very
you
much.
next time. Thank you. Y'all have a great day.